So in this video, I'd like to continue with our discussion on buffers. In the last video, we talked about a couple of the limitations of buffers, and that one of them is that when you're making a buffer solution, you can only buffer a solution at a pH which is close to the pKa of the weak acid that is in the buffer. All right. For example, if you were to try to make a buffer using acetic acid, as the weak acid in your buffer, you could only make a buffer solution that had a pH of between 4.3 and 5.3, right? And that's because the pKa of acetic acid is 4.76, and that's the only pH region that you're going to have significant amounts of both the acid form and the conjugate base form of that particular weak acid. All right. Once you get about 1 pH unit higher, you're only going to have the conjugate base. Once you get about a pH unit below that, you're only going to have the acid form. All right. And remember, for it to have that property of being able to absorb either the acid or the base, you have to have both of those. All right. But the thing is, it's not like we're out of luck, because if we wanted to make a buffer at a different pH, we can do that. We just can't use this particular weak acid. All right, so let's investigate that. So the question is, what weak acid could we use to make buffer solutions at the following pHs? All right, so let's say that we wanted to make a solution that had a very stable pH of 3.75, something that if you made it, if you added a little bit of, a drop of HCl, its pH wouldn't drop that much. Or if you added a drop of NaOH, a strong base, its pH wouldn't rise that much. All right. Well, to figure out how to make this buffer, we need to identify the appropriate weak acid that you could use to make that buffer solution. All right. So the way we're going to do this is we need to find a weak acid that has a pKa of roughly around 3.75, which is the desired pH buffer we want to make. Right? So the way we can do this is to take a look at the data booklet. All right, and if you look at the data booklet and you're looking through all these weak acids that they put in there with their pKa's, you can find here at the very top they've got a weak acid that has exactly that pKa. All right, so methanoic acid, it's also known as formic acid, has that pKa. So that would be an appropriate weak acid that we could use to make that. So that would be the appropriate weak acid. All right. So I'll let you go through. If you want to take time, pause the video, see if you can look through that data booklet and find the weak acids that would be used to make one at 10 and one at a pH of 2.9. All right. So for pH of 10, hopefully you would have looked in there and seen there's this chemical called phenol. All right, and it's got a pKa of 9.99. All right, which you'll notice is pretty darn close to 10. All right. One thing I want to point out is that you can make buffers that are at pHs that are close to this number. All right, so we could make a buffer that had a pH of probably 3.9 if we wanted to, using methanoic acid, because that pH is close enough. If it's within, I would say, plus or minus 0.2 or 0.3, you would be able to do that. We'll talk about why that's possible later. All right, so what about 2.9? Again, looking around, there's actually two selections that you could find. There was one that had a pKa of 2.87 and one that was exactly 2.90. Either of those could be used to make a buffer at that pH. All right. So how do we go about making a buffer solution? All right. So up here, we just saw how to select an appropriate weak acid that you could use to make a buffer at these pHs. But does that mean that that the way you make this buffer solution is you just add some of this weak acid to water. All right, and the answer is no. It's not quite that simple for the following reason. All right, so for example, we just saw that if we wanted to make a buffer solution at a pH of 3.75, we would use methanoic acid. All right, but if you think about it, we already know enough from the past to be able to demonstrate that simply adding methanoic acid to water would not give us a buffer solution at 3.75. All right, and hopefully you can maybe predict this, but like if I were to just say, what would the pH be of a solution if you added, let's say, 1 mole of methanoic acid to 1 liter of water? All right, well, hopefully you realize that question comes back to something that we did a long time ago, which is just calculating the pH of a weak acid solution. All right, and if you recall the way we went about that, we did it by setting up this start, change, end calculation. Let's say that we added 1 mole of that to a liter of water, or to make a total of 1 liter solution. We would start with this this concentration right here. We know that this acid-base dissociation is going to occur right here. We would start with that theoretical starting point. We know that some of this reaction is going to occur that would that would involve the reducing of this by a certain amount, that would increase these by certain amounts, and we could calculate what these end concentrations would be. All right, well, we know what the pKa is of methanoic acid. From that we could calculate its Ka. All right, we could set its Ka equal to, well, we know that the Ka is equal to this expression right here. All right, that comes from this reversible reaction right here. Setting up the plugging in the values that we had for those into that expression right there, we end up solving for x, and we know that x equals the concentration of H3O plus, and that's what we can use to get the pH. All right, because the pH is nothing but the negative logarithm of the hydronium ion concentration. All right, so we could calculate that the pH of that solution of methanoic that you would get simply by adding a certain amount of methanoic acid to water will give a pH of 1.88. All right, so that raises an obvious question. Why are we saying that you could make a buffered solution, a solution that has a very stable pH of 3.75 using methanoic acid, if a solution of methanoic acid would have a pH that's very different from that desired pH that we want to get? All right, and the answer is to recall what an ideal buffer is. All right, remember that an ideal buffer is a solution that contains a 50-50 mixture, not just of the weak acid, but a 50-50 mixture of the weak acid plus its conjugate base. All right, and if we just simply take some methanoic acid and we add it to water, we wouldn't have a 50-50 mixture of the acid and conjugate base. We would have a solution that contains mostly just the acid form. All right, remember, it's a weak acid. Weak acids are acids that only partially dissociate when you add them to water. All right, so if we want to turn this into a buffer, what we need to do is we need to turn some of the HA that's in the solution originally and convert some of that HA into A-, so that we get to that 50-50 mixture. All right, and so the way that we're going to go about doing this is take advantage of this simple acid-base reaction right here. If you react HA with OH-, you're going to end up getting A- plus H2O. All right, well, so here's the thing. Let's just take this hypothetical here. Let's pretend that in the solution, obviously in that solution, we're going to have millions of HAs. All right, let's just focus on, let's pretend that we only had 4 of them in the solution. All right, what would we want to do if we wanted to make a buffer? All right, well, we can take a look at this reaction right here. So if we add if we were not to add any OH minus. All right, essentially what we'd have is pretty much all HA. All right, yes, we would have a little bit of A minus because some of this right here would get created just by reacting with water. But you know, even when you make this solution, it's still mostly this amount right here. All right, so you know, we're going to oversimplify just by saying we're going to have all this right here. All right, so conversely, if we added 4 molecules of OH minus, we would end up turning all 4 of these into A minus. All right, and that's not what we want to do either. All right, remember, we want to have a 50-50 mixture of them. All right, so what do we want to do to that origin? What would we want to do to that solution right there to turn it into a good buffer? All right, what we would want to do is we would want to react 2 of these guys with OH minus and do nothing to 2 others. All right, and the way that you're going to do that is if we calculated that, for example, if we had 1 mole of HA that we had added to the water, we would want to add half a mole of OH minus. All right, because if you had half the amount of OH as you did this, it's essentially like you would be reacting it with half of the molecules present. All right, there's not quite enough OH minus to react with all 4 of those, and what that would end up creating is 2 of these would react and make A minuses. All right, and these are the 2, and just I'm just forwarding them over here. There's not enough OH minus to react, so you still have the HA swimming around. And notice what you have there. All right, you would have a 50-50 mixture of HA and A minus. All right, so by reacting 1 mole of HA with half a mole of OH minus, you're going to achieve that ideal solution. All right, so for example, if we had 2 moles of HA here, we would want to add 1 mole of OH minus. That's half the amount of the HA that was originally present in the solution. All right, and so so this is the overall strategy, and it might seem that like if we wanted to do this, what we need to do is we want to calculate, you figure out the amount of HA that's in the solution and calculate the exact amount of OH minus that we need to add. All right, and that is one way that you could go about doing this. All right, but there's a better way to do it. All right, and here's what we're going to take advantage of. All right, I say there's a simpler way. This is going to might sound kind of complicated at first, but if experimentally, in terms of how easy it is to make this buffer solution in a laboratory and make sure that it's precise, this is actually a better way to do it. All right, and what we're going to do is we're going to take advantage of that equation that we talked about a little bit earlier, that Henderson-Hasselbalch equation. All right, which says pH equals the pKa plus the log of A minus over HA. All right, so again, this is the pH of whatever your solution is. This would be the pKa of some weak acid. So for example, if we're talking about for methanoic acid, all right, it's got a particular pKa. All right, so if we've got a solution containing methanoic acid, the pKa that we use here would be 3.75 because that's the pKa of methanoic acid. All right, but we know that in that solution we could either we're going to have a certain amount of the HA form, which is this, and a certain amount of the A minus form, which is this right here. All right, and so that's what these are right here. This would be the conjugate base. This is the acid form. And so what this equation shows is if we change the pH, which you could do by, like, let's say we added a couple of drops of either HCl or OH minus or hydroxide. How would that affect the relative ratios of these? All right. Well, so this is a really useful tool for figuring this out. So if we wanted to have a solution that had a 50-50 mixture, all right, so I'm going to take a break there and finish this in the next video.